Okay, so hi everyone. Welcome to another webinar on dimensional management by Creaform Engineering. So as you might already know, the subject of today's presentation will be modifier symbols. So I know this is a subject that is quite specific, but if we think about it, modifier symbols can be found in most of the drawing and they can have an important impact on the cost and functionality of a part. So it is still important to know, have a good understanding of their uses and signification, and that's what we will do today. Also, by the way, on the webinar windows, you should see a button somewhere where you can click to ask a written question. So if you have questions during the presentation, don't hesitate and to use that function, and we will try to answer all the questions at the end of the webinar. So today we will be two presenters. At the moment, it's Cedric speaking. So let me introduce myself quickly. So I currently work for Creaform Engineering as a dimensional management analyst. I have a technical degree in aerospace engineering and a little more than 8 years of experience in the practical application of GD&T and dimensional management concepts. My background comes mainly from the aerospace and railway industries. And as you can see on the screen, I will be accompanied by Paul. Paul, do you want to introduce yourself a little bit?
Good morning, everyone. So my name is Paul, and I have a background in mechanical engineering. And then I worked a few years as a project manager in a food processing plant in the engineering department with a special focus and interest on quality management. And so I've been then transitioned to Creaform, where I've been working in the metrology services department.
All right, thank you. So just before attacking our main subject, I'll quickly present Creaform. So Creaform is a large team of 260 technical experts and 600 employees that are spread across 10 countries. And here we can see how we are structured. So as you can see, Creaform is part of a larger company called Ametec, which acquired Creaform in 2013. And on the Creaform side, we are split in multiple divisions, as you can see. Usually the most known division is the technology division, which develop all the instrument and 3D scanners that you see on the screen. And then in the other division, we have the metrology services, which Paul is part of. So the metrology services are dealing with everything that touches to inspection, quality control, 3D scan, things like that. And the last division, which is probably the least known, is the engineering services. So on that slide, we can see all the services that Creaform Engineering offer. So we will not go into the detail for each of them, but we can see that they are still broadly spread across the entire product development process. So we can offer support that goes from the design phase up to the production. And we can see here in the middle, in the rectangle, there is dimensional management, which is a pretty big subject that include, amongst other, the notion that we will talk about today. So if you have not seen the previous webinar, we remind you that they are all available on the Creaform Engineering website in the news sections. So for those that would like to take a look, you have the address here in the bottom right corner. That also includes today's presentation, which is currently recorded, and the link to the recording will be emailed to you in the next few days. So just a quick review of the agenda for the presentation. So for today, we have chosen a few examples of typical case that we see most often in most of the designs. And for each of them, we'll start by having a look at the purpose of the symbol in the standard. So what we might want to use that symbol. Then we will look a bit at the way we should use and interpret it. And finally, we will also talk about the control of these parts. So amongst other, what impact will the choice to use or not use the symbol will have on the inspection and control of these parts. So if we bring back the small diagram showing the different steps of dimensional management that we had in the previous presentation, the current one will show a small portion of two subjects, so the GD&T language and the inspection. So here we have most of the modifier symbols. So there's a lot of them and we can find them at a lot of places in a drawing. And the reason why we use them is simple, is to have a geometric description on the drawing that is as close as possible as to the true functionality of the part. So as close as possible to reality. So as we spoke quickly in the first webinars, the reason why we insist on having a definition that is as exact as possible of our tolerance is because we want to avoid rejecting parts if they are good. and lose money, or we want to avoid introducing non-functional parts to the assembly line and potentially cause a production stops. So today we will focus on the two symbols that are at the top of the list, the maximum and least material modifier. So from these two symbols, we will be able to derive 4 typical use cases. And the reason for that is that the same symbol can be applied either on the tolerance zone, like we can see on the left, or we can apply it to the datum, like in the 2 examples on the right. So depending on where you put it, the same symbol will not necessarily have the same meaning. So we will look at them in detail using concrete examples during the presentation, but just to give you a starting idea of typical use case, the maximum material condition modifier will often be used to avoid a contact between 2 parts, so to avoid a clash. The least material condition modifier will mostly be used to protect the minimum wall of material that we want to keep at all time between 2 features of a part. The maximum material boundary, this one will be a bit different. We will use it when we have a datum on which we can attribute a size, like a hole or a groove, for example, and that we have the right to use the play that the size of the datum will create to better locate the part or best fit them during the assembly. And the least material boundary is also when you have a datum that have a size, but this one will mostly be used when we want to protect a minimum of material around that datum. So said like that, for sure, it's still very abstract, but don't worry, it will become clearer as we go through the examples in the next slides. So to do that, we will once again use the same assembly that we used in the previous presentation, our ATV suspension. We selected 3 parts in the assembly that each present a typical use case of a modifier, and we will look at them one by one and explain every time the purpose of the symbol in each situation. So the first case that we have is the maximum material condition modifier. So as we said a bit earlier, when the M symbol is attributed to the size of the tolerance zone, like we can see on the top right, it will often be to avoid an interference between 2 parts. So to illustrate this, we will look at the hole pattern that makes the connection between the gray and the yellow part right here. So the way that this interface works is that we'll ensure a contact between the gray and the yellow part using a tapping bar, so that the purple parts underneath. And what we have to understand here is that only the tapping bar will have threads, and the other part on top will only have clearance hole to allow for the passage of the bolts. So if we take a cross section, we see that what we just described is a quite common interface configuration where we want to clamp 2 or more parts together that have a clearance hole using another part underneath that have a thread. So for this example, we will focus on tolerancing the clearance hole in the yellow part. So what we want to avoid here is to have a hole that is so out of position that it will create an interference with the bolt and prevent its installation. So to avoid that, what we will do is we will define a position tolerance on the hole pattern. So concretely, what this tolerance box will do is to define a cylindrical tolerance zone around the axis of the hole, and the size of the tolerance will be defined by the value that we put here in the tolerance box. So once that is done, we will be sure that as long as the axis remain inside the cylindrical tolerance zone, we will be able to install the bolts. We'll never have a clash. But the thing is, in real life, the diameter of the clearance hole will never be perfect. So sometimes it will be smaller, sometimes it will be larger. So let's look at an example where the hole is larger, like this, for example. So in reality, this means that we could allow for the whole axis to go slightly outside of the tolerance zone, like this, and without creating an interference with the bolt. So this is where the M symbol become interesting. So what this symbol will do is that it will create a link between the size of the hole and the size of the tolerance zone in a way that the larger the hole will be, the larger the tolerance zone will be as well. In our case, it would look a bit like that. So it also means that if we are in a situation where we have a part that failed in inspection because the position of the hole is out of spec, but the tolerance on the diameter of the hole could allow us to increase its size, we will be allowed to re-drill the hole larger in order to gain a position tolerance and possibly bring back the part in tolerance. I think we can all agree that in most cases, it will be a lot easier to just increase the size of a hole instead of trying to correct its position. And in a case like this, where what we have is a clearance hole, the thing we care about is really to avoid an interference. So it makes perfect sense to allow for the hole to be drilled a bit larger in order to correct for a small error in position. And that is what the M symbol will communicate in that case. So now that we understand the concept that the maximum material condition modifier will be used to create a link between the size of the hole and the size of its positional tolerance, we can add value to our example to see how it works in practice. So let's say that the diameter of the hole is 11 millimeter plus or minus 0.25, and that we have a positional tolerance of 0.5 with the small MMC modifier. So what the symbol means is that the tolerance of 0.5 needs to apply when our hole is at its maximum material condition. So in the case of a hole, we must be careful. The condition in which there will be the most material on the part is not when the hole will be at its maximum diameter. It's when the hole will be at its smallest possible. So in other words, in our case, when the diameter of the hole will be at 10.75, this is the condition where we will have the most material on our part, and this is where the tolerance of 0.5 will apply. So that is what the symbol means. Then the more the diameter of the hole will move away from our maximum material condition, the more the tolerance zone will enlarge. So for example, if the diameter of the hole is 0.1 larger at 10.85, our tolerance zone will also be 0.1 larger at 0.6. So, and the same principle will continue to apply until we reach the maximum diameter allowed by the tolerance on the drawing. So that's about it for the concept and theory of the symbol. So I will now let Paul talk a bit more about the practical aspect of what the symbol implies for the inspection and control of the parts.
Yeah, so here's what the real component would look like on the right side. And then on the left side, we see the 2D drawing, which we'd get, say, from the engineer or from a client, which would serve as the reference for our inspection. So let's zoom in a bit on the 2D drawing. And you'll notice on the top right, on the pattern of 8 holes here, we applied this MMC or maximum material condition for the position tolerance. And so as Cedric mentioned, we're able to calculate the hole at its MMC, which is when it's at its smallest diameter. So in this case, it would be 11 minus 0.25, so 10.75 millimeters. And so this means that at 10.75, we're allowed a tolerance on the position of 0.5 millimeters. And as the hole grows bigger, and so goes away from its MMC condition, we gain proportionally some bonus tolerance on the position. So here we'll showcase this inspection in our VX Inspect module, which is a part of the Creaform suite of software. And so this module specifically, VX Inspect, is used, as the name would suggest, for inspections. And so what we see here shown in blue, this is the mesh that we'd obtain after scanning the actual part in real life. And also present in the module would be the CAD drawing, so the nominal CAD reference, which is not shown in this snapshot, but it's also present in the inspection. And so VX Inspect allows us to align the data, which can also come from probe points, but in this case, obviously, it's a scanned mesh. And we can align it to the reference CAD either by best fit or via a datum alignment, such as is the case here. And so the interface of VX Inspect is fairly simple. And the reason for that is the philosophy of the software is to allow for operators which may not have that much experience in GD&T to carry out inspections relatively easily. So let's come back to this example specifically. Here we're just showing a couple of the holes, so holes 5 and 8, just to better understand what's going on. And notice right now, there's no M symbol applied to the tolerance. So we'll first look at the example in its default state, so regardless of material condition first. And notice, obviously here, the red X's indicate that these holes are out of tolerance. So they are failing the inspection. They are not passing as is. So let's show this simplified diagram that we made just to better understand and see what's going on. So right now what you're seeing is everything in the perfect ideal scenario. So nothing is deviating. These dark blue pins would represent, say, inspection pins that would be part of the inspection jig. So in reality, what we have is that the holes 5 and 7 here, they deviate both in diameter, as you can see, and position. And what we saw is that they were actually failing the inspection. And here, obviously, it's a bit exaggerated, but that's just to show visually what's going on. And so just remember that the diameters of the holes, they are acceptable. So the diameters pass because they fall within this 11 plus or minus 0.25 millimeter specification. So the diameters are actually around 11.22. However, when we add the position callout, as we can see, with a tolerance of 0.5 millimeters without any bonus, we need to increase the size of these pin gauges 5 and 7, proportionally. And so we see that the holes fail in this scenario. And so why do we need to increase the inspection pins in this case? It's because otherwise you'd allow the hole to move more than 0.5 millimeters out of position if you kept them the same diameter. And in fact, the diameter of the pin should always be 0.5 millimeters smaller than the diameter of the actual or the real measured hole. So let's jump back to our VxInspec module window. This time we added the M symbol in the inspection program. And notice that the deviations haven't changed at all. So all the numbers are identical to what they were. So the X, Y, Z, the diameter, the deviation itself, nothing has changed in that regard. However, in this case, the holes do pass the inspection. And that's because we now have a bonus on the position. And so you can see the bonus is around 0.47 millimeters, and the total tolerance is around 0.97 millimeters. And just if you want to do a quick calculation again, just to help you better understand where this number is coming from, as Cedric mentioned earlier, we can essentially calculate this number by subtracting the hole at its MMC condition, its maximum material condition, which in this case would be 11 minus 0.25, so 10.75 millimeters. And we subtract that from the actual measured diameter, which is 11.229. So that gives us this bonus number here, 0.479 millimeters. And to add 0.5 to that, we'll get the total tolerance of 0.97 millimeters. So if we go back to the schematic here and look at our example again, and this time we'll be adding the MMC. So what happens when we add this MMC symbol is that all the inspection pins now, they shrink down, they narrow down in diameter to the virtual condition of the holes. And what we mean by virtual condition, we can calculate it here. In this case, it would be 11 minus 0.25. So the MMC of the hole minus its positional tolerance at MMC. So 10.75 minus the 0.5, which gives us a 10.25 millimeter diameter pin. So that's what the virtual condition of the hole is, what we're talking about. And so now we can see visually that these holes do pass the inspection. And so the good thing about MMC is that it often gives us the possibility to use rigid physical jigs to inspect the parts. Because once the drawing is specified, the virtual condition of the holes and features in general, they don't change. And so it doesn't depend on the measured deviation of the hole. Now, a word of caution is that sometimes we want to avoid MMC. So for example, here, in this case, we would introduce maybe a bit too much imprecision or inaccuracy in the assembly. And so it's always essential to define the functional role of a part early on in the design and better understand if you're able to allow for extra play or not in the assembly. And if not, obviously you'll leave out the MMC. And so that pretty much wraps up the first example of maximum condition. So I'll pass it back to you, Cedric.
Thank you, Paul. So next one. So our next example will be the least material condition modifier. So if you remember what we said at the beginning, a typical use case for that symbol is to protect a minimum wall thickness on our part. So what we have in front of us is a casted part with some machine surface being shown in blue. And what we want to ensure in that example is that a minimum thickness of material is always present between the big machine diameter and the outside surfaces of the casting. So to better understand what is happening, we will make a cross-section of our part like this. We will then trace in blue the machine surfaces, in purple the casted surfaces, just to better see them. And we will also illustrate the minimum thickness of material that we want to protect at all time in red hatching, like this. So we already know that the casted surfaces will deviate. So this is something that will happen and there's no way to avoid it. But the feature on which we want to focus today is the machine hole, the positioning of the machine hole. So to control the position of this hole, we will once again use a positional tolerance box. So as in the first example with the clearance hole, that requirement will define a cylindrical tolerance zone around the axis of the hole. And we can define the size of the tolerance in a way that will ensure us that as long as the axis of the hole remain within its tolerance zone, the minimum wall thickness won't be affected. But once again, in real life, the diameter, a hole with a perfect nominal diameter is not something that exists. So in this case, we can imagine that the hole diameter is smaller than nominal, which will look a bit like this. So when we do this, we quickly realize that the position of the axis can leave a little bit the defined tolerance zone without necessarily affecting the wall thickness that we want to protect. And this is what the L symbol here will authorize. So when we write the L symbol beside the size of the tolerance zone in our tolerance box, that will mean that the smaller the diameter of the hole will be, the larger the tolerance box will be. So as you probably understood, this is exactly the opposite of the M symbol that we had in the previous example. So a bit like we have done in the previous example, we will now attribute some value to our tolerance. So let's say that the diameter of the hole is 50 millimeter plus or minus 25, and that we have a positional tolerance of 0.2 with the small L modifier. So what this means is that our tolerance of 0.2 needs to apply when the diameter is at its least material condition. So for a hole, once again, we must be careful. The minimum material condition is not when the hole is at its minimum diameter. So the situation where we will have the least material on our part is when the hole will be at its largest diameter. So in our example, this means that when the diameter of the hole is at 50.25, this is when we will have the least material on our part, and this is where the tolerance of 0.2 must apply. So then it's the same thing as with the maximum material modifier that we have seen already. The further we move away from that diameter value, the larger our tolerance zone will be. So if the whole diameter move away from the minimum material value by 0.1, for example, and become 50.15, our tolerance zone will enlarge by the same amount, so 0.1, and become 0.3. So the size of the tolerance zone will continue to grow relative to the diameter until we arrive at the minimum diameter authorized by the drawing. So again, I'll turn it over to Paul to talk to us about the practical side of this interpretation.
So again, we'll conduct a real analysis on this component using this 2D drawing on the left. So if we zoom in on the drawing, we'll notice that on the bottom right-hand side, we apply this L symbol, the LMC symbol, to the hole with the 50 millimeter diameter. And so as Cedric mentioned, we can calculate the least material condition of the hole when it's at its largest diameter. So in this case, it would be 50.25 millimeters. And at its least material condition, this means that the hole would have a maximum positional tolerance of 0.2 millimeters. And as the hole shrinks and gets further away from its LMC, we are able to gain a bit of bonus tolerance on its position. So once again, let's jump back into our VX Inspect window. And we'll first examine this example without the LMC symbol. Okay, so as you can see, there's no L applied. So we're just in the regardless of material condition for now. And we can see that the value of the deviation is 0.4 millimeters. And of course, that exceeds the maximum tolerance of 0.2 millimeters. And that's why we have this red X, because this part is currently not passing the inspection. So again, we prepared this little diagram to better explain what's going on in this scenario. And so right now we're seeing the ideal condition where nothing deviates. And you can see the red dotted line here. This represents the minimum boundary that we wouldn't want the hole to infringe, because we don't want this boundary to become too thin. Now in our case, the real hole actually deviates both in diameter, it's smaller, and also deviates from the central axis in position. And of course, we exaggerated it once again, just to show you visually. And keep in mind, again, that the diameter does fall within tolerance. So the diameter of the hole is within this 50 plus or minus 0.25 specification. In fact, it's around 49.76 millimeters. So the diameter is okay. However, when we add the GD&T position callout without the LMC, we need to reduce the diameter of the boundary proportionally, as such, proportionally to the actual size of our measured hole. And so as a result, in this case, this part would exceed the boundary and would fail the inspection. So if we go back to our VX Inspect window, this time we did add the LMC callout, as you can see, the least material condition. And notice also that none of the numbers have changed. So still the same position deviation, still the same diameter. So all of that is exactly the same. But now that we have this bonus tolerance, the same part that was otherwise failing previously now passes the inspection. And the bonus itself is 0.485 millimeters. And that actually comes from the difference between this real measured value, which is 49.76, and the LMC condition of the hole, which in this case would be 50 plus 0.25, so 50.25. So 50.25 minus 49.76, that gives us this bonus. And then the total tolerance, we add to that this 0.2, which is the base tolerance for this position callout. So let's go back to the diagram once again with our new situation. So still the same hole, still the same thing that's going on, but now that we've added this LMC callout in the box, we now give ourselves this constant 10 millimeter safety net around the boundary of the part. And so as long as this hole doesn't exceed the boundary while still maintaining an acceptable diameter, obviously, then the hole would pass the inspection. So again, a word of caution with LMC. Sometimes in a case where you want to ensure an easy fit between two components, you certainly would want to avoid using LMC, because this modifier doesn't guarantee any clearance, and we could end up with quite a tight fit, as you can see here. So for instance, in this example, the orange tube would have quite a hard time sliding into the board central hole. So keep in mind that LMC is used a lot less than MMC in drawings. And so you have to be a bit more careful applying it. And so that pretty much wraps up what we had to say for the least material condition. And so let's look now at the last practical scenario.
Thank you, Paul. So our third and last example will be a bit different. This one, because as you can see on the top right corner, this time the symbol will be applied to a datum instead of being applied to the tolerance size like we have seen in the two last example. So to illustrate this, we have chosen to use the assembly between the wheel hub and the brake disc. So to understand how the disc is installed to the hub, we'll make a section and a zoom like this. So what we see here is that the disc in gray seems to be located by the big diameter in the middle, and then we have a pattern of 4 holes that will serve as clearance hole for the passage of the bolts that will screw in the hub and clamp the two parts together. So schematically, it would look a bit like this. So first, the disc will be placed on the hub like this. And now what is locating the disc from left to right is the big diameter at the center. So it's true that it seems a bit strange to say that it is the big diameter that is locating the part with what we are seeing on the screen right now, because there's a lot of play between the two parts. So it is certain that in real life, the fit between the two diameter will be a lot tighter. So that's important if we want to use this feature to locate the part. But in this case, we voluntarily increase the gap between the two parts just to illustrate the concept. So now, once our two parts are in contact, nothing is preventing us to use the play that between the two datum that we have to slide the gray part and align the whole pattern in order to be able to install the bolts. So what this means in regard to the positioning of the whole pattern in the gray part is that if we have a situation where all of the holes are offset by the same amount in the same direction relative to the datum, so a bit like this, we will still be allowed to use the residual play between the datums to try and realign the bolt pattern of the two parts, which would look a bit like that. So the thing that we should not forget when we do this, on the other end, is that the size of the datum can still vary. So we understand that the smaller the datum will be on our gray part, the less play we will have available to come and reposition the parts like this. So, and also in addition to that, our datum could also have an orientation error. So the hole could be produced at an angle relatively to the contact surface and look a bit like that. And now we can clearly see that an orientation error will also reduce the play that we might have available to realign our parts. So what we need to understand here is that contrary to the other examples, when the symbol is applied to the datum, it won't necessarily translate directly to a bonus tolerance on individual holes. Instead, it will allow us to move the whole part around and try to best fit all the requirements using the residual plate that is created by the size and orientation of a datum. So we should not forget also that when determining the amount of available residual play, we must not only consider the size of the datum, but also its orientation. So once again, it's Paul's turn to tell us about how we control the parts that make use of this modifier.
Yeah, so in this example, we see that on the 2D drawing in the bottom left-hand side, we specified an M symbol on the datum B this time. And so as Cedric was saying, this represents the maximum material boundary. And so we can calculate the value of this boundary. It's essentially the 73 millimeters, which is the nominal diameter of datum B, minus the 0.5 millimeters, which is its tolerance on diameter, minus 0.5 millimeters again, which is the tolerance on the position. And so we get this number 72 millimeters, which is the virtual condition of that datum B. So let's jump into our VX Inspect software once again. And here, as the previous examples, we're comparing the scan data of the physical parts to the nominal CAD. And so right now we are omitting the M symbol. Okay, so we're just going to look at the example regardless of material boundary. Okay, so in the default condition. Now notice that all the holes currently are failing because they deviate more in position than their allowed tolerance of 1 millimeters, right? So this one, for instance, is deviating 1.2 millimeters. So they're all failing the inspection. Notice also that their diameters are all within acceptable ranges. So they all fall within the 10 plus or minus 0.2. So we have a couple holes or a few holes that are bigger and some that are smaller. So following the same logic as before, we'll just show you a more simplified diagram of what's going on in this scenario. So first, again, we'll show what's going on without any modifier, so no MMB. And so we see that in our case, the real measured holes, they deviate somewhat in position and in diameter from the perfect ideal scenario, as we can see here. Now we also need to adjust the pin simulators proportionately to the diameter of those real measured holes when we come to add this positional GD&T callout. And so a couple of them will widen according to the holes, and a couple of them will narrow down. And so we can see at this point that the inspection obviously fails. Now, if we jump back to our case in VxInspect, and this time we're going to add the maximum material boundary callouts on all four circles, as well as we added MMC too in this case. So Cedric touched on this briefly, but I will repeat this to make sure it's a bit clearer. The MMB, which is applied to datum B, does not add any numerical bonus value to the tolerance. So all the bonus, which for example, in the case of circle 1 is 0.305 millimeters, all this bonus is coming strictly from the MMC applied to the position here. And if we want to calculate it again quickly, it's simply as we did in the first scenario, as in the first example, we find the MMC condition of the hole, which is 10 minus 0.2, so 9.8, and we subtract that number from the measured value of the hole, which is 10.105. So that's where we get this number of 0.305 millimeter bonus. And the total tolerance, we add to that just 1 millimeter, which is the base tolerance. So all the bonus is coming strictly from the MMC, not the MMB. And in fact, if we were to remove this M symbol from the datum B, we'd still have the same bonus value. So now, if you were paying attention, you might have noticed that the position values have changed in this example. And so all the X, Y, Z values have also changed. And that's because this modifier on datum B allows us to shift the position of our real measured data relative to the datum inspection frame. And so if I show you a quick little animation, you'll see the effect of the alignment shifting as we allow this this extra play coming from the datum B, thanks to the MMB datum modifier. Now, obviously, in that example that you saw just now, it's not deviating that much because the real deviation is less than a millimeter. But that shows you a bit what's going on in the actual software as we apply this MMB to datum B. So let's go back to the schematic with the real holes deviating. Now, thanks to the MMC symbol, this allows us to manufacture the inspection pins at the virtual condition of the holes. And then with this modifier on datum B, so the MMB, it allows us to simulate a datum which is fixed at its virtual condition, which we calculated earlier to be 72 millimeters. So if you can take a look at this little animation, it's just showing you how it gives us play to come and refit the part relative to the inspection jig. And so now the same holes that previously were not passing the inspection now pass the inspection thanks to these datum modifiers. again, we want to be careful sometimes because in certain assemblies, we can't afford to have this imbalance, say on a central axis where a part might be rotating at high speeds. And so again, it's always necessary to establish the functional definition of a part even before thinking of using any GD&T modifiers. And so that pretty much wraps it up for that last example. So to recap what we saw today, again, I'll reiterate, we use GD&T modifier symbols to optimize the number of parts considered acceptable without sacrificing their functionality. And it's always critical to define a component before deciding to apply these symbols. So first we saw the maximum material. In general, this modifier makes assembling easier, and we use it often for clearance holes and clearance fits. So for instance, it's used often for assembly hole patterns. Next, we touched on the least material. So in least material, this is usually used when we want to preserve a certain boundary. And like we mentioned a couple times, it's used a lot less frequently in drawings, but it still has its uses, especially maybe in a stress zone of a mechanical assembly where we want to preserve a certain wall thickness. And last but not least, by default, we have what we call regardless of feature size or regardless of material condition. And that's when there are no M or L symbols applied to the tolerance. So in general, this is more restrictive, but at the same time, it's a bit more conservative. And in this case, the position and the size of the feature are independent. So to conclude, what did we see today? First of all, poor geometric definition may lead to rejecting parts that are actually functional. So it's always important to define the function of a component early on in the design stage. Next, we saw that with modifier symbols, we can clarify the practical definition of a part or an assembly. And so it helps us a bit understand what's going on, and practically speaking, in the drawing. We also saw that the meaning of a modifier symbol can change depending whether it's applied to an entity or a datum, as we saw in the case of MMC versus MMB. And finally, in the case of MMC, it often allows us to use physical inspection jigs, and so it can help to reduce quality control related costs. So that concludes the main presentation on GD&T modifier symbols today. So we hope this was useful for clearing up any confusion around certain topics that are not always so intuitive. And also just a little reminder on some services that Creaform offers. So we offer some workshop style GD&T training. We also offer a lot of support ranging from engineering and product development to pre-production and in-production support. And don't forget also, we have a lot of metrology services. So we're talking about portable CMMs, scanners, part and assembly inspections, training on our equipment, reverse engineering, and so on. And so thank you again for your attention today. And we'll transition now to the question period. So if there's anything that wasn't that clear in our presentation, now would be the time to ask us.
Yeah, you can also ask general questions about the modifiers if there's something we didn't cover. So don't hesitate.
Yep.
So, okay. Question. So yeah, the first question was about the recording of the webinar. So yes, the webinar is recorded. A link to the recording will be sent to you in the next few days. So this exact same webinar is recorded. So in the question we have this one. So what represents zero tolerance at MMC?
Yeah, so that's a good question. Do you want to go back, Cedric, to the slide, the first example where you were calculating Like
This
you were
one?
calculating yeah, that's the one. So we could, it would be almost equivalent if we were to replace this 0.5 tolerance with the M symbol with a 0 M, and then change the diameter of the hole. So essentially the tolerance we'd allow to go down to 10.25 millimeter diameter. So what's happening, we could essentially shift the tolerance on the position to the diameter. And so in some cases, like on the shop floor, maybe you're confident in drilling precisely located holes, but you're not as confident in drilling the proper diameter of a hole. So you can sort of shift tolerances between diameter and position. And essentially 0 at MMC would give you the maximum number of parts that could, in theory, pass inspection without compromising their functionality. But that also means that if you're at the minimum diameter, which is 10.25, then you'd have to have perfect precision on the location of the hole.
All right. I have another question here. Is someone is asking about an example for the LMB situation.
Yeah.
So the L modifier, but applied to a datum.
Yeah.
So this
So
one we didn't cover. That's true.
yeah, that LMB is quite a bit more rare than LMC and obviously MMC, MMB. Sometimes we use it to maintain a certain wall thickness, say for a sleeve feature. And the other thing to keep in mind is that
I have the
LMC and
example
LMB.
there.
Yeah. Okay, there we go. Yeah, so this is an example of a sleeve where we want to conserve that minimum wall thickness going around. It's pretty rare. I don't know. Have you seen it that many times in your experience, Cedric? An LMB on a drawing?
I almost never seen an L on a datum, but I think that's one of the example where we could have it.
Yeah.
Let's say we have a datum that is on a diameter like this. If the datum is at its smallest, this is where we have the tolerance, and as it becomes larger, we give more play on the positioning of the parts to achieve the tolerance that we have here.
Yeah.
So that would result in a certain wall thickness that will be maintained at all time between the inside diameter here and the outside diameter here.
One thing I'll add also regarding LMC and LMB is that you can't really inspect it with a physical gauge, as is the case with MMC. Usually you can only calculate it using mathematical methods or through software. And that's even specified in the ASME documentation itself. So it's a bit more difficult to inspect. You can't really do it with a physical jig.
Yeah. Another question that just come in, does calculating tolerance using MMB require the software, or it can be done by hand? Well, I think it can be done by tooling, right? Using a gauge.
Yeah, so we showed, say for example, like in the third example, go maybe to like the diagram or something. We showed that essentially you can have an inspection jig with inspection pins and fit it on and see if it fits. And also for datum B, you can simulate it. In fact, in software, often what will happen is that it simulates these datums, but you can obviously do it in real practical life as well. So especially with MMC and MMB, it allows you to create these pins which have a fixed diameter at the virtual condition of the holes. So you already know just based on the 2D drawing what those diameters are going to be. And so you can already manufacture an inspection jig without actually knowing how the real part deviates in reality. Whereas without MMC, if you're just inspecting with no M symbol, then those inspection pins, you'd have to increase or decrease the size of their diameter depending on the actual real measured holes. So not as convenient. Yeah.
So maybe a last question here. Is it possible to apply MMC on threaded holes?
It is possible in theory. It's not usually recommended. I've never seen it in my practice. I don't know about you, Cedric, but it's not usually recommended because typically it's difficult to measure with accuracy the position of threaded holes. You can do it like with flexible hole location gauges, but usually it's not worth the trouble, and you're much better off applying it on actual like more measurable parts.
The amount of bonus we will gain by that is very small also. So it's kind of it's possible, but not that.
It's not worth the trouble.
Yeah, exactly, not worth it. So that concludes the presentation for today. So again, thank you for participating. Also, when you will leave, there will be a survey at the end. So please take a few minutes to answer that survey. We use the answer that people write down there to orient our choice for the future webinar. It's always interesting to see what you think. And thank you. Have a nice day.
Thank you.